but do I. This constant is due, and it's in a negative direction, is due to diffusion current. This is due to the difference in charge carrier concentration across the diode. The exponential is due to drift. This is due to voltage. It gets much higher, and there is a limit. You cannot, if you try to put this many volts across a diode, you will get exaamps. This region right here is called the breakdown region. It doesn't involve smoke and flames. It is actually kind of like a reverse bias diode. They use this for voltage regulators. This is also called V-Zener.
It's like
a Zener diode.
It's the diode from that one circuit we did in 490 last semester that had the diode that's running current going back the opposite direction.
No, that's called a flyback. If you see this symbol in a circuit, this is a Zener diode. Yeah. You use it for a voltage regulator. Yeah. It's part, and you just have to buffer it really good in order to get a good solid voltage on the output. Okay. The built-in potential. Oh, okay, sure. We just did this in 280, so I figure like you guys just did this yesterday. To calculate the built-in potential of the junction, V0, it's KT over Q. K is Boltzmann's constant, T is in temperature in Kelvin. Q is the charge on electron, times the ln of P on the P side over P on the N side. We can also use this and get it directly from the doping levels, and this is the more common form of this equation. KT over Q, the ln of the doping on the N side times the doping on the P side over Ni squared. And Ni is still 1.5 times 10 to the 10th per cm cubed. And all of these calculations are in my slide solutions. I feel like at this point with seniors, you can fill in the numbers, especially because I don't want to do it on here. This one's pretty straightforward. This equation has a got you in it. No, it doesn't. It's okay. This one doesn't have a gotcha in it. You don't have to be so careful with this one. If we want to find the width of the depletion region, the width that this charge is accumulating around the junction, you can fill in these, you just fill in the things in this formulas. One thing you got to be careful with here, I see people mess up a lot. When it says epsilon SI, this equals the relative dielectric coefficient times epsilon naught. And for silicon, this would be 11.7 times epsilon naught is 8.854 times 10 to the minus 14th. You have to use the version of that that is in, what is it, farads per centimeter. Is epsilon naught. So that's the only issue kind of right there. I see on the calculations. This one, to find the junction capacitance, it's basically epsilon A over D, and that is going to be the, we want the junction capacitance per unit area. So this becomes, you know, you start out with the basic equation, this was on the exam. The basic equation for capacitance, epsilon A over D. What I really want to calculate is the capacitance per unit area. So that just becomes epsilon over D. And so the distance is the width of this depletion region. Again, epsilon S is epsilon relative to epsilon naught. And you can plug all the numbers in there. None of those are really weird. It just takes a little tedious with the calculations. No, this isn't the one with gotcha. The one you have to worry about is when you're using area, because the area is usually in, the area they give you is in nanometers squared or micrometers squared. You have to convert that back to centimeters squared because things in here are always referenced back to centimeters. Always. Okay. I really want to go on. I know I only got 10 minutes, but I think this will go fairly quickly. What am I doing? Am I insane? I'm trying to rush through this. We can start it, and if I don't feel like you do a good job, we can do it again on the next class. Okay, we want to look at the MOS structure. When we're talking about the MOS structure, what I mean here is the MOS capacitor. We have a gate up at the top, we have some oxide, and we have a substrate. I'm not worrying about the drain and the source. This is just going straight through the gate, and we want to look at that capacitive effect. The reason why is we want to be able to understand what's contributing to the threshold voltage. Really big deal. If I want to lower my operating voltage on my chips, I've got to lower those threshold voltages. So we got to figure out ways to do that. And they're getting smaller and smaller. So we're going to look at an energy band diagram through this dotted line. This is the area I'm looking through, not the MOSFET itself. This is the MOS capacitor. And what I have here, if I'm thinking about the energy levels, I've got a metal, I've got an oxide, and then I've got a semiconductor. So this is the substrate, and then I've got the oxide. The metal is usually quoted in terms of the thing we're looking for is the work function. And this work function is how many electron volts does it take to get an electron out of this material and up to the vacuum level, which is the electrons now floating around in free space. It's left the material. That's what this level represents, is the vacuum level. This is an amazing slide to look at when you're doing the homework, because you can actually calculate things by just using this part of it right here. For an oxide, it takes a smaller amount. It has a huge band gap here, 8 electron volts, and it takes a smaller amount of energy to get you up to the vacuum level. Inside the semiconductor, now I've got the conduction band, I've got the valence band, the intrinsic Fermi level, which is halfway in between, and this must be p-type because the real Fermi level is lower than the intrinsic Fermi level. We have the built-in potential Q phi. I think what are we doing on the homework? Q phi m minus Q phi s. Okay, so the built-in potential energy of the junction is going to be the difference between this number and this number right here. And Q phi s represents how much energy it takes to get something from the Fermi level up to the vacuum level. So this is going to be a kind of a key for this. The flat band voltage, which is a major component of the threshold voltage, is going to be the difference in energy on the metal side versus the difference in energy on the semiconductor side without the Q in front of it. This will be in volts, this will be in electron volts. If I can get the flat band voltage down lower, I can lower the threshold voltage. How do I do that? I can mess around with the Fermi level here. I would call this slide up when you're going to get a problem on homework 4 that tells you to calculate Q phi s. I would pull this slide up because you can do it by, if you look at this, I could take this number right here, which is a constant for silicon. I could take the band gap, and I could just do this by numbers. Could figure out what this is. I've got the various links in here. This is how I solve the problem. is I basically said, okay, Q phi S is going to be this distance plus this distance plus this distance. And yeah, you can figure it out that way too. You don't necessarily need formulas. This is a good slide to look at. Oh, I know what I really want to get to. So we get separate materials in here. Q phi M, Q phi S is the, with the whatchamacallit, this, with the silicon dioxide acts like a barrier. I have one level of doping in Na1. I have nearly getting close to degenerate doping in Na2, and I have a metal on the backside. This region is more heavily doped, is all you're asking for there. Okay, so when I draw the band diagrams across here, I've got to take all these separate Fermi levels as reference to the vacuum level, the little dotted lines here. And my convention is I have to line them up to draw the band diagram. So when I line that up, it's going to take those bands and it's going to put these little bends in there. And what I want to do in order to turn on the turn on the transistor, I have to get past the threshold voltage. I have to get, this is why they call it the flat band. I've got to take this and give this a little bit of energy going up and give me a flat voltage across there. See, I got to flatten that band. That's why they call it the flat band voltage. And it is the biggest contributor to the threshold voltage, which we will do in the next class. Let's see, 3 minutes. Accumulation, that also means it's really cut off.
Very cut off.
Very cut off. This is an NMOS. VGS is less than 0. I basically, even my P-type substrate, I have P-type materials going across there. And these band diagrams. And then I have another region, depletion. This is sub-threshold. I've actually have negative charge carriers that are starting to get next to the forma channel. VGS is less than the threshold voltage, less than V flat band. It's not enough to turn it on. You do get leakage current. If you really want that transistor to be off and not leak, you've got to put VGS being negative or VS higher than VG. So they start to deplete and the current starts to go up exponentially. In inversion, which is both triode and saturation, VGS is greater than VT. A channel forms, allowing a path for current to flow, and those bands flatten out. And then deep depletion, it's just a transient effect that we don't talk about a lot. And I think I'm really done. I just do want to point out at this point, because it's class is ending, but when you're doing the homework 4, look at this. These are really good slides to reference because there are pieces of the solution for homework 4 in these slides. The numbers may be different, but the formulas are there.
Good to know.
That is good to know. Okay.
Which slides are these?
These are the semiconductor physics, 09, yes. And this will be what homework 4 is on. I think homework 5 is mostly flash. Yeah.
Yeah, there's one question on the pre-lecture flash that I just thought I couldn't find.
Okay, what was it?
What was it?
Pre-lecture. You get.
I tried it like yesterday and clicked the link and it just said,
Oh, there is a reading.
The
link is broken, but most of it's in the Michelonian part of whatever the book.
She has the download of the book.
Nolan, are you here? I'm gonna check roll real quick. Nolan is not here. Shujan is never here. He watches the videos, and Yuhao is the same. Okay.
Yeah, I think what is it? Oh no, it wasn't that I could find the readings, but that I didn't understand the question.
Okay, so I've got them right here. Pre-lecture 6. Which one was it?
It was,
Hold on, we're getting within 6 feet of each other.
soon I'll be completely vaccinated, we don't have to worry about.
Yeah, but the rules are still the rules.
Until Doug Ducey opens this.
All right.
This is the,
But CDC recommendations would be in our favor.
this one up here.
Match up one term, program erase.
Yeah, I didn't understand what it was. Match up one term from each.
That's what Dr. Farrell. Program means you increase speed threshold. The cell stores a 0. You're adding electrons. And erase means you decrease speed threshold. The cell stores a 1. You remove electrons. So you create 2 coherent sentences out of that word jumble. Right there.
Okay. Do you think you could change the due date to midnight so I can redo that question?
Is that not a question? The worst chance.
Fair enough.
Okay.
I did just want to include the note in my home, so I don't